me start my recording. Okay, so I also want to pin my video. Okay. Has anyone looked to see if they can find the exam in Blackboard yet? Or do I need to show you where it is? I can do that. Let's see. Yeah, okay. So let's share this screen and then go back to Blackboard. Let's go in here like this. Okay, so there's the course. And under exam 1, and they're all going to be like this from now on, so I only need to show you once. So you should see an exam 1 for all students. And it's open now. And you just click on that. And then, unfortunately, you have to click again. You could get to the exam here, right here. But I wanted to go deeper and show you how to submit the exam. You go into that folder, then you have the ability to attach the file once you've completed the exam. And there's a copy of it right there. And if I click on that, it should come up in the browser. But you can't complete it there. You have to go over here to, let's see. And it's telling me to sign in over here and download it. All right. So you got a brief look at it, the first page anyway. So you need to download it onto your computer before you start to work on it. And a large part of it is you'll be able to fill in just like the review document. Right? It's a fillable form, and you can save it. So you can do as many of the multiple choice as you want, so you don't have to do the whole thing by hand. And then once you finish, save it and print it out and finish it, because there's going to be some where you have to actually write it in. Unless you're really good with Office tools, or no, not Office tools, with Acrobat tools. So once you have it completed, and you can take a photo of it, convert it into a PDF preferably, and then attach it here to, and down here in the right hand corner, it's covered up for me. There it is, submit. Okay, any questions about that part?
Do you want us to show our work on it? Or can we just like do it on a notebook and then write the answer in there and just send it as an attachment?
Showing your work, let me see. Well, let's see. I believe every answer is only 1 point. So showing your work wouldn't make a difference. If I have questions that are multiple points and you show me the work, and then I can see whether you're on the right track and give you partial credit. But in this exam, every question or every part of a question is worth 1 point. So you either got it or you don't. It's digital. It's either a 0 or a 1. But in the future, there are some problems in exams that are multiple points. And if you can show me your work, then I can see if you don't get the correct answer, then I can go back and look and see if you're on the right track and give you partial credit. Of course, with the bonus questions, you need to show me your work. And I don't think there's probably not any bonus on this one. I don't believe there are. Because in chapter 1 and 2, this stuff is fundamental. In other words, if you don't know the chapter 1 and chapter 2 material really well, then the rest of the course is going to give you fits. This is basic stuff. Okay. So any other questions? And let's see, I'll unshare this one, because I'll only need to use the whiteboard for review. And of course, the way I always do this is, if you're having trouble with any one of these review problems, I'm going to let you start the ball rolling, because I don't want to get to the end of the class and not have covered one of your concerns. So I open the floor first, and we'll start off with your concerns or problems, and then if we have any time left, I'll do some talking. And of course, as we go, if something comes to mind that you didn't think of in the beginning, then you can interrupt me, and we'll be sure and get your problem answered. Okay, anybody have any specifics, or have you got that far? I hope you've gotten sort of into the first few pages. That would be nice. Because chemistry is not something that most people can cram for. If you've got a course where it's simple memorization and nothing more, then cramming might work. You know, it can use mnemonic devices and memory tricks for exams, but for this stuff where you have to learn how to solve problems, and you're learning a new vocabulary, actually, you got to do it little at a time. Okay, any specific problems that we need to deal with before I just jump into the review document and start talking? Okay, we don't have to finish all of these today. In fact, if we get through chapter 1, that's fine, because we'll have next Tuesday to finish up chapter 2, as far as review goes. What I've noticed is with this camera is a lot higher than the other one was. So when I think I'm looking at you, I'm actually looking at my screen, and you're up there. So it may look a little weird. Okay, nobody's having specific problems? All right. So let's look at some basic stuff to begin with. How about, well, we just start with number 1 on page 1. Which of the following is an example of a quantitative observation? Understand the difference between quantitative and qualitative. Qualitative is an observation of a nebulous quality. Quantitative means there's usually a number associated with it. A measurement has been made. So if you look at those choices, the only one that fits is D. The temperature of a liquid is 60 degrees centigrade. That is quantitative. You've got a number and a unit of measure. Okay. Number 2 refers to the difference between a law and a theory. And in fact, the reference here is observations of natural phenomena. So that's why the answer is not simply just a law. Observed behavior that can be formulated into a statement, sometimes a mathematical formula about the nature, about something in nature, is a natural law. In fact, the founders of this country referred to natural law quite often. Only theirs was a little different than our concept of natural law. So I won't go into that. So the difference between law and theory is one word, actually. So to get from here to here, you ask yourself why. The natural law just says, this is what happens if these are the circumstances, that this is the input, get the same output every time. That's why so many of the laws are formulas, like Newton's second law of motion, force equals mass times acceleration. That's a natural law. It doesn't say why it happens. No, it just says, if you know the mass of something and you know the force applied to it, then it's going to accelerate at a given rate every time, the same way, every time. Doesn't matter whether it's on the Earth's surface, it's in outer space, or it's on Jupiter. It'll always happen the same way. Now, of course, the force is unbalanced. If there's a force acting against you, then it's only the force that's in excess of the balance. But that's a law. Now, Newton himself struggled with the why things happen. He had 3 laws of motion, and then he followed it up with the law of universal gravitation. But he never could come up with a theory that explained why bodies attract one another. It wasn't until relativity that we were able to say, well, with a degree of certainty, why things attract one another. And it was Einstein that came up with that one. But it's always that key word, why, is the difference between the two. Okay, how about unit conversions? You need to have a grasp of the fundamental units of at least length, which would be meters, mass, which is kilograms, volume, which is liters, time, which is seconds. And then there are a few others, but those are the ones that we want to focus on for now. These are fundamental units. All the other units are derived. And in order to derive the units, you need a prefix. For instance, we rarely, even in the countries that subscribe to the metric system, only certain things are measured in meters. Other things like the speed of your vehicle is not in meters per second. It's actually in kilometers per hour. Okay, so if you're driving, maybe, I think the rough estimate is if you're driving 55 miles an hour, you're going 100 kilometers an hour. Now, has your speed changed? No. If I'm going a certain number of miles per hour, I'm still going the same speed, whether it's measured this way or this way. So the physical reality, the speed, is the same. It's just the measurement is different. That's why you can convert from one to the other, because you're not changing the physics or the chemistry of the process. But this prefix, kilo, means 1,000. So instead of 1 meter, there are 1,000 meters per hour in this measurement. So you need to know those prefixes. Now there's one exception. This fundamental unit, kilogram, already has a prefix. And the reason for that is that grams was inherited. It's a historical mass. But when it was standardized, a gram was too small to standardize a mass. If you had a standard mass of a gram, it's like that. And if you had just a tiny scratch in it, the percentage error would be huge. So they had to go to a kilogram, which was, much larger. And any small deviations in a kilogram would be would not be so massive. So that's still the fundamental unit. So from this point, if you go to that, this is 1,000 times smaller than, this is 1,000 times smaller than that. But the rest of them, you have prefixes that start with the fundamental unit and go from there. So meters could go to millimeters. Milli means 1,000th of. Now, another concept, if you get confused about the size of a measurement and its relationship to some other measurement, if the absolute size of the measurement goes down, right, goes down from a meter, right, millimeter is smaller than a meter, then the number of the smaller units that are within the larger unit goes up. So if the size of the unit goes down, then the multiplier goes up. So in other words, if you have 1 millimeter, you have 1,000th of a meter. But if you're starting with 1 meter, then to go down to a millimeter, you need 1,000 times. Okay? So they go opposite one another. All right, so let's get back to the problem. Which of the following metric relationships is incorrect? All right, so we look for, the first one is 1 microliter is 10 to the minus 6 liters. So 10 to the minus 6 is what? It's a millionth of. Right? 6 zeros in the denominator of the fraction is 10 to the minus 6. So A is correct. 1 microliter is 10 to the minus 6 liters. 1 gram equals 10 to the third kilograms. So if we say 1 gram is equal to 10 to the third kilograms, flashing lights ought to go off in the back of your eyeballs when you see something like that. 1 gram is smaller than a kilogram. So if you multiply the kilogram times a large number, you're going to be even further from reality. In fact, this should be over there. It takes 1,000 grams to make 1 kilogram. So, test-taking technique. In a problem like this where you have multiple choice and one of them does not say all of the above or none of the above or A and B or A and C, those types of tricks, if they're all unique answers, then once you work your way down and you find the answer, stop, write the answer, go to the next question. Save yourself some time and trouble. We found the answer, it's B. Okay. How about number 5? Order the 4 metric prefixes from smallest to largest. All right, let's see if we have all the same in each of the answers. Nano, milli, centi, and kilo. Yeah, they're all the same. So let's take the first one. So nano, milli, centi, and kilo. Okay? So how do we put those in order? Well, there are a number of ways to approach it. My favorite way is when you have an ordering problem, I like to bracket it in. I like to locate the smallest one, locate the largest one, or whatever the parameters may be. Find one end and the other end, and then fill in the middle, right? So what's the biggest unit here? If we're going from, smallest to largest. So the largest prefix would be kilo. It's 1,000 times, right?
That'd be A.
yeah, it's A.
That's what I thought, but I just didn't want to say it.
And then you look at what's the smallest one. Well, centi means 100th of. Milli means 1,000th of. And nano means 1,000,000,000th of. Okay, so a nanometer, a nanometer is 1,000,000th of a meter. It's very, very small. So this nanotechnology they talk about in the popular, in the press and in science reports, they're talking about particle sizes that are extremely small. Let's see, while we're here, well, okay, so smallest to largest is that, and it's A. I usually write the problem numbers up here too, so I better start doing that. So that's number 5. Actually, it's chapter 1, 5. We're missing one that is really useful, and that's the one that goes right in here. So which one is that? You remember? Micro. And micro is 10 to the minus 6th, or 1/1,000,000th of. So a micrometer is 1/1,000,000th of a meter. In fact, we have devices that are called micrometers because they measure in very, very, very small increments. Has anybody had a course where you use a microscope? Nobody's had, yeah. Okay,
Yeah.
so one of the exercises, at least the first time you use a microscope, one of the exercises that they're supposed to give you is to calibrate your objectives. And you use a slide that's got lines etched on it. You put the slide under there, and then you set the power on your microscope, and you say, all right, you've got these arbitrary lines that are in your eyepiece, and then you're focusing on the slide that's calibrated. And then you can measure you can calculate the magnification that way. Well, you can do it with the objective and eyepiece too. So if you have a 10 power eyepiece and a 10 power objective, you have a 100 power magnification in your microscope. And then you can use that calibration, that slide that you put in there, and say, okay, I know the distance between those two lines on the slide is this, and they correspond to certain lines that are etched in the eyepiece. You can say, at this power, these two lines are so many micrometers apart or millimeters apart, depending on your power. Right, so I digress. Okay, let's see. That was up through number 6. I want to hit stuff that's really important. Okay, here's a simple unit conversion. Number 6. Unit conversions sometimes give students trouble. And many textbooks don't approach it logically. The authors think they're doing it logically. And at a certain level it is, but in my mind, it's incomplete. Okay, let me just put it that way. So I'm not going to hammer on any one author and their textbooks because they published a book and I haven't. But number 6 says 8.1 kilograms is how many grams? Okay, so there's your starting point. This is a very simple problem. You're given the starting point. It's not like a 3-sentence word problem where you have to pick out where your starting point is. That's why I'm using this one, because it's easy to get started with. How many grams does that represent? So we need to go from here to grams. So what do you need? You need a conversion factor. Remember when we discussed conversion factors, or I talked about it, we didn't really discuss it. I talked about conversion factors in the lecture. I told you what a conversion factor was and how it is derived. You always start with an equality, right? So in this case, our equality would be kilograms and grams. So how many grams does it take to make 1 kilogram? It takes 1,000 grams to make a kilogram. So how do you get a conversion factor out of that? Well, you divide both sides of the equation by one or the other, depending on which one you need in the denominator. We need a kilogram in the denominator, right? That's how you cancel the kilograms, because you don't want to end up with kilograms over here. So we got to get rid of them. So we need kilograms on the bottom. Okay, so this is equal to 1, right? A number divided by itself is 1. A unit divided by itself is also 1. Don't forget to divide the units, because that's the heart of dimensional analysis, is the units of measure. So this is equal to 1. We can multiply this times 1, no problem. But that won't get us where we need to go. So we're going to use the equivalent of number 1 is this one. Now we're talking. Kilograms cancel. Numerator, denominator. Remember, when you write a number or a unit by itself and no divisor sign, it's always in the numerator. That is a numerator. So the numerator here is canceled by the denominator. And what do we have left? We got grams left. That's what we want. In the numerator, in the numerator. Now we set the problem up. The rest is just number crunching. So 8.1 times 10 to the third grams should be our answer, which is B. Okay. Now, I went the long way around explaining that just as a refresher. But when you're in the heat of test taking, you should be able to, in your mind, skip this part and just say, I need to cancel this. I need to be left with that. So this is on top, this is on the bottom. And those are for problems where you know a single conversion factor. Right? This one was easy. That conversion factor is simple because of the prefixes. Sometimes you have conversions that require multiple conversion factors. I call them chained. We chain them together. But the same process operates in converting from here to here, even if you use 2, 3, 4, 5 conversion factors. And we'll probably get to one in just a second, and I can demonstrate what I mean by that. I was just checking to be sure I was recording this thing. Okay, so let's see. 7, that's a simple one. 8's a simple one. Okay. This refers to a definition. The definition of something, which is the answer to the question. So the question says, what is the measure of resistance an object has to a change in its state of motion? This goes back to Newton's first law of motion. He said that an object at rest tends to remain at rest unless it's acted upon by an external force. Or an object in motion tends to remain in motion unless acted upon by an external force. Now, why is that true? It's true because of a word that was invented to apply to the amount of the substance. So an object that's this size and an object that's this size made out of the same stuff, this one will have more of stuff than this one does. And this one has more mass. Mass is the key term there. Why do we use that definition and not a feeling of a pull? Because a feeling of a pull is not mass, it's weight. A mass in Earth's gravity at the surface of the Earth, 1 kilogram mass experiences a pull of about 1 Newton. But there's a difference between weight and mass. The weight depends upon the gravitational field. So I would weigh 1/6 as much on the surface of the moon as I do here on the surface of the Earth. Actually, I weigh less in Beckley than I would in Myrtle Beach, because we're about 2,600 feet high here, which is further from the center of the Earth, and you're at sea level, Myrtle Beach. So I should weigh fractionally less here than I do at Myrtle Beach. Okay, so I beat that horse enough. The answer to that one is A. Mass. All right, let's see. Okay, we can talk about the difference between, and this comes from question 10, but we'll expand on it. Yeah, we'll expand on it. You know the difference? Well, you probably, the definition is easy. Accuracy versus precision. So we got any hunters here? Okay. Before you go out stalking a deer, you got to be sure that your gun's shooting straight, right? You want it to hit where you aim. And one of the things you do is zero your rifle in at a given yardage. And you can, whatever yardage you think you're going to be needing in the field is the one you choose. You know, if you like to get really close, you may only zero at 100 yards. Or if you don't like to get so close, or you can't get close, then you may zero it in at 250 or 350 or 400 yards, you know, if you're that good a shot. But the way you do it is you fire at least 3 shots at a target at the distance that you want to zero. And you see, where do they impact, right? Very often, with today's rifles and ammunition, they're so reproducible, you're going to get, you might get like this. You might get 3 off like that, right? Now that's assuming that you don't have any significant wind impinging on your bullet as it flies that would throw it off. But that would be good precision to have a grouping like that at 100 or 200, 300 yards. So what do? Well, once you've determined that your precision is good, now if it's not that good to begin with, you need to deal with the precision first. Maybe you're using bad ammo, you know, old ammo, or I don't know, maybe you bought the wrong kind. Maybe you've got a 223 and you put NATO 5.56 in it. You know, that's dangerous, because 5.56 operates at a higher pressure. So if you put it in your 223, it might blow up in your face. The other way around is okay. You can use 223 in a M16. Anyway, other factors. So you need to deal with the other factors to get your grouping down. Now, once you've got a good grouping or precision, then you make adjustments to your scope to bring it this way and that way. And then once you've got that grouping on your bullseye, you've got both precision and accuracy. Because accuracy is how close are you to the bullseye, and precision is how close is your grouping. Okay, that anybody that's a shooter understands what I'm talking about. And hopefully the point is made for others who are not gun enthusiasts or hunters. I'm not a hunter, but I have worked with guns over the years. And even just target practice is fun. Actually, I had better luck with pistols than I did with rifles. And a whole lot better luck with pistols and rifles than shotguns. For some reason, I never could hit a moving target. I didn't practice enough, of course. But that's another topic. Okay, any questions about precision and accuracy? It's pretty straightforward. Let's take an example. Let's say that you have 4 measurements of mass of something on a balance. And let's say, I don't know, 2.53, 2.49, 2.51, and 2.50 grams. Okay, I have 4 measurements. All right. Now, what does that look like to you? Does that look like precise? Looks to me like it's fairly precise. Right. So let's say, what's the average? And that's the term for average. Whenever you see an X with a bar over it, that designates the mean. Anybody going to take statistics? No? Nobody taking? Okay. That's how you write the mean, or the average value. So if we take that one and do an average on it, let's see what we get. Okay, so rounded off, I get 2.51. Now let's say we have use a different balance, and we get 2.63, 2.40, 2.51, and 2.30. Now that looks to me like it's less precise than this one. You have a wider scatter, okay? Okay? So, the average of this one is 2.46. So, they're pretty close together, not too far apart. But the precision of this one is way, way off. So, that's an example of actually going into the lab and making measurements where you have good reproducibility here, which is another word for precision, and poor reproducibility here. If you get numbers that bad in the laboratory, then you probably want to look into the balance. The first, is your balance suffering from some malady, some electronic malady, for instance? Or is there something in the lab that's interfering with the accurate measurement? Now, we can't tell accuracy here because we don't know what the accepted value is. But if the accepted value were 2.50, this one would be closer. Okay. All right. So we got about a half hour left. Let's see if we can move on to some more. Let me look toward the end of chapter 1 problems and work backwards to be sure I'm not missing something. So I don't want to miss out. I'm going to get chapter 1 today, for sure. Okay. Let me find one where we need to use a chained conversion. And then we'll move to a different topic. Okay. How about number 37? Okay, 37 says the pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. Okay. What's the pressure when expressed in grams per square meter? So we're headed here, grams per square meter. Now, what many textbooks will show you is a single conversion where you have this term in the numerator and this term in the denominator. And that's a valid approach if you know the conversion factor. but we don't necessarily know the conversion factor. In fact, the problem gives you some conversion factors, right? And you're supposed to work from there. Okay. When you have a number with more than one unit of measure in its make, you do one at a time. So let's start with pounds. Let's convert pounds to grams first in the numerator. Okay, conversion factor they give us is 2.205 pounds is 1 kilogram. All right, we can work with that. Okay. Now, what have we just done? We've changed from standard measure to metric, which is good because metric operates on base 10. And to go from kilograms to grams is really simple. Like that. Okay, so now we've got grams. We're done with grams. Now we can work on square inches. Okay, so how do we do? I'm going to have to come down here. So down here, we want to convert inches to some metric unit. And they're giving us a value of 2.54 centimeters is 1 inch, right? So inches is in the denominator. That means to cancel it, inches has to be in the numerator for our conversion factor. Okay, 2.54 centimeters is 1 inch. Okay, but what's the problem here? That's inches to the first power. This is inches to the second power. So how do we deal with that? Well, what if we square that whole expression? What does it do? It squares this one to cancel that one, and it squares this one. But what else does it do? It squares that one, and it squares that one. Okay? So that will help us get rid of square inches, but it leaves us with everything else squared. Okay, so don't forget to do that if you use this method. Now we've got square centimeters. We've got to go to square meters. So what's the conversion from centimeters to meters? 100 centimeters in a meter. But we just squared that centimeter. So we're going to square this one too. So that gives you square centimeters and square meters, which is where we want it to go. Grams per square meter. But I'll say it again, don't forget to square the units as well as, the numbers as well as the units. Okay, so that should get us down to square meters. And we should have grams per square meter. Now what we have to do is crunch the numbers. So how do you do it on your calculator? Well, I do all of the numerators times each other, and then I divide sequentially, divide by the denominator. So 14.7 and 1,000 times, and 1 times, and what's 10 squared is 10 to the 4th, correct? So that's 10,000 times. Now come down to the denominator, 2.205, divided into that, and 2.54 squared. Divided into that. That's it. So that should be 1.0, 3 significant figures, times 10 to the 7th. Okay, let's see if, is that one of the answers? 37. No. Oh, okay, here we are. Yeah, B. So that's B. Now I want to make another point here while we're on the subject. How did I know that that was only 3 significant figures? Because the original number is 3 significant figures, and every one of these conversion factors is an exact number. All conversion factors are exact numbers. So you don't have to worry about how many significant figures are in your conversion factors. If you do a chain conversion like this, the only one you need to focus on is the first one. Right? That's the limiting one. 3 significant figures. 3. Okay? All right. So that was 37. Now let's move on to something else. Okay, we're getting into density here. This is still unit conversions. All right, I think I got time to do this one, and we can. Yeah, I think we can do this one and still have time to do one more. Yeah, I'm kind of torn between 45 and 46. 45 actually uses the density expression. Yeah, let's do that one. 45. Okay, so here you have a word problem, and you need to, with word problems, what I like to do is I pull out the information that's given and put it on the whiteboard. Okay, so we're given 20 milliliters sample of glycerol. 20 milliliters of glycerol. Okay? And this 20 milliliters has a mass of 25.2 grams. Okay? So this is the volume, this is the mass. What's the density in ounces per quart? So the expression density operates here. And you have a mass, and you can divide it by a volume, and you get 20.0 milliliters. Oops, my mistake. Mass, 25.2 grams per 20 milliliters. Okay? Now, we don't have to divide that out because the question is, what is that density in ounces per quart? So we got to convert this to ounces and this to quarts. So we might as well just keep going with our chain. So let's do mass first. So 1 ounce equals 28.4 grams. 28.4 grams is 1 ounce. So that gives you ounces. We're done for mass. How about volume? Volume, we'll bring it down here. 1 liter equals 1.06 quarts. But that's not liters yet. So this is in the denominator. That has to be in the numerator. Okay? So we got rid of milliliters. Now we can use our conversion factor. 1.06 quarts is 1 liter. There we go. So now, all you have to do is, we've analyzed the dimensions and made sure that they're right, ounces per quart. We started with our density expression, and now all you have to do is the math. Run the calculator. And the answer should be A, 41.9. All right. So I'm going to cut this one short because I want to be sure and get through everything in chapter 1. We got temperature conversions. That's just a formula. Maybe 2 formulas. Right? If you're going from Fahrenheit to Kelvin, you got to convert Fahrenheit to centigrade first, then add 273 to get Kelvin. Okay. All right. There's some discussion about mixtures, right? And here's one that might give you trouble. Rather than draw this one up there, maybe sharing it would be easier. So what I need is the document. Okay. Just a second. We ain't got enough time to get it up here. I'll share this in just a minute, as soon as I get the document up. Oops, wrong one. Here we go, there. That's what I get for having a complex directory folder structure. Exam1. And then we need review. Okay, so let me share this one. Okay, so there we have, there's our review document, and come on, there we go. Going down to 70 through 73. There we go. So we have these diagrams, and let me make that bigger. Get that out of my way. I want to zoom in a little bit so we can see the details. Let's go up to 200%. That's better. Okay, so you can see these 5 different representations of possible mixtures. Now I say possible because they may not all be mixtures. So when you go to answer the question, which best represents a homogeneous mixture of an element and a compound? Right, so we have to take that sentence apart. There needs to be an element and a compound in the container. So elements are represented by single circles or squares of a different color, either a solid or a gray. So with an element and a compound, we look for the ones. These are all elements. They're separate. These are all elements. Those are all elements. These are all compounds. So the only one that's an element and a compound is this one with a square and 2 circles of different colors bound together. Right? So that should be a dead giveaway there. And if you look at it to see if it matches, that's homogeneous. Right? So this one, the answer to 70 should be E. 71 is which best represents a gaseous compound? What characterizes a gas? Well, a gas is one in which the parts of a gas, the particles, are very far apart. So that lets out B and lets out D. And then you look at a gaseous compound, right? So this one can't be it because we just identified it as a mixture of an element and a compound. These look like both gases, A and C, because things are very far apart. But A is individual particles. There are no compounds there. Whereas C has this small gray circle with a large white circle. That's your compound. So the next one, 71, is C. Which best represents a solid element? Okay, a solid element. Which one's an element? Well, an element has to be one type of particle, right? Can't have a mixture. So this one has one type of circle, a gray circle, right? And it looks like it's a solid because you have regular arrangement of atoms very close together. And besides, D is the only one that's close together, but it's got a mixture of whites and grays. So that lets out D. So B has to be the answer to 72, solid element. Which best represents a heterogeneous mixture of 2 elements? All right. So 2 elements. Well, let's see. Here's let me read that again. A heterogeneous mixture of 2 elements. All right. 2 elements. Let's see. That's compound. That's pure substance. Can't be. This is compound element. That can't be. So it's either A or D. A heterogeneous mixture of 2 elements. All right. So we do have 2 elements in both A and D. We have the gray circle and we have the white circle. But which one is heterogeneous? Remember what I said about, well, I hope I said, about gases. All gas mixtures are homogeneous. Every one. A gas mixture is always a solution because there's plenty of room for everybody. They can evenly distribute themselves throughout. So that leaves the gas out. This heterogeneous mixture, D, is the answer. All right, so D for 73. Okay? That's my logic. Okay, let's see. I'm going to unshare that one. There we go. And now we can look at possible others. How How do you deal with significant figures? I've only got 5 minutes left. There are two rules, remember, for significant figures. Right? You have the multiply-divide rule, and you have the add-subtract rule. The multiply-divide rule is simple. It's just that you multiply or divide all the factors, and in your answer, keep all the decimal places that your calculator gives you. Even if it's a multiple step, keep them all from start to finish. Then at the end, you take that number and you compare it to the factors that went into the calculation, and the least number of significant figures determines how many you can keep in your answer. So if your calculator says your answer's got 9 significant figures, but the least in your calculation is 3, then you have to round it down to 3. The add and subtract is a little different. In that case, you line up the decimal points, or where the decimal points would be, if there are any. And then you say the shortest one from right to left determines the extent of the answer. So let's say we have, let's do 77. Calculate this one. $5.123 plus 0.033 divided by 1.650. Okay, what's the problem with this one? You don't know which order. Do you need to do this one first or that one first? Well, if you don't have any parentheses to direct your operations, you have to go back to the accepted order of operation. Everybody remembers that from math class. PEMDAS. Parentheses, exponents, multiply, divide, add, subtract. So we don't have any parentheses. We don't have any exponents. So do we have any multiplies? No. We do have a divide, right? So we have to do the divide first. So 0.033 divided by 1.650 equals what? This one we have to do in stages. 0.033 and 1.650 divide. So this is in scientific notation. Now, how many of these places can we keep in our coefficient? Well, this is a divide, so we use the least number, which is 2, right? Zeros to the left don't count. So that's 2, and we have to round it to this position, 2.0 times 10 to the minus 2. Okay. Now, since we're gonna, the next operation that's left is add, we have to add this one to that one. This one needs to be converted to standard notation so we can line up the decimals. You can't line these decimals up because part of the number is buried in the power of 10. So this is going to be 1, 2 to the left. So that's the standard number for this one. Now notice that we have a 0 out there. We get to keep that one because that's significant. All right, now we do this one. 1, 2, 3, 4, and 0.020. Right? What's the limit on the answer here? This is an add number. 1, 2, 3. we're limited to that. So let's add them together and then round them off to this position. 4 is less than 5. So our number is 5.143. 77, 5.143 is C. Okay? I picked that one out because you have to use this accepted order of operation. If you don't, then one of those other numbers would be add this one and then divide by that one. And that would be wrong. And that's the stealth of multiple choice questions. The people who devise the multiple choice questions, if they're half worth their salt, will go in and say, what kind of mistakes can a student make with this problem? And they'll run the problem with those mistakes and put that as one of the answers. So if you do it wrong, you may find your answer there, but it's still the wrong answer. Right? So you have to be careful and work the problem correctly. Okay, it looks like to me like we're out of time. And we pretty much covered chapter 1. So this is Thursday. Tuesday, we'll look at chapter 2 review. And this afternoon, in about 13 minutes, I'm going to come back at 2 o'clock with my personal Zoom ID. And we're going to look at I think it's my personal. I may have put a link, or I put a Zoom link in CHEM103. So go to CHEM103 and find the Zoom there, and link in to that one. This is voluntary. I'm going to go through the second lab, the Excel lab, during that time period. And it'll be recorded, so if you can't make it, that's fine. So I'll see you back at 2 o'clock, and we'll pick up with the Excel lab. Any questions or comments before we end this one? Okay.
No, sir.
Okay. We'll see you at 2 o'clock if you want to be there. It's voluntary.
Thank you.
Bye-bye. Stop the recording.